All right, so after plotting our basic linear probability model and plotting the raw data and some binned averages, we're now moving on to actually graphing our logit coefficients and in particular graphing the fitted logistic curve in addition to the raw data, okay? Just to go back, we were talking about an example where we're predicting vote choices, so support for the Republican candidate in the 2000 US presidential election. And the main predictor that we're just looking at right now is ideological identification, feeling closer to conservatives or closer to liberals, okay? And our model output that we estimated previously, which we called M2A, is just a standard logistic regression with just one predictor. Okay, so in order to kind of graph that logistic regression, that logistic curve, first what we have to do is we just save our intercept and the slope coefficient that we estimated in a tibble so we can use it in ggplot. Okay, so first we have our intercept, and this is of course the first element of our coefficient vector. Okay, and then since we only have one predictor, we have one slope coefficient for the feeling thermometer, and that's the second component, the second element of our coefficient vector. Right now we're just focusing on the point estimates themselves. Okay, and then we pipe all of this to a ggplot where we will map on the x-axis our intercept and on the y-axis our ideological feeling thermometer. Okay. And then what we're going to do basically is just in this plot, rather than just plotting the raw data, here we're just plotting the coefficient, the point estimates for the coefficients themselves, right? And just to give an additional visualization for the parameter for the intercept and the parameter for the slope. Okay, and we're going to use that later on when we basically proceed to visualize uncertainty around our estimates. Okay, so here we just have basically the point estimates for the intercept and for the slope, or the coefficient for our predictor and the intercept itself. We add some vertical and horizontal lines for those point estimates as well, and add then just basically one individual point for our point estimate. Okay. We've seen a similar plot in the context of linear regression as well. You'll see the kind of the parallels in a second. And then the second plot that we are going to create here is basically an extension of the initial plot 2 that we created here, which is basically just the scatter plot of our outcome measure on the y-axis and our predictor on the x-axis. Okay, so we already saved this here in P2, and we're basically using that in our next ggplot command, and we're just adding additional layers, additional components to that plot. Okay, and specifically the elements that we're going to add is just two separate two separate layers. One is a function where we basically, as a function, insert both the linear predictor, so this is the intercept, plus our beta 1 coefficient times our independent measure, which is x in this case. And all of this is plugged into the inverse logit function. So we're basically computing the linear predictor and then plugging that into the inverse logit function to compute the predicted probability. Okay, we're having some additional arguments to kind of adjust the layout and the style, and then we add an additional text label where we basically just print the regression coefficients and the underlying link function in the plot as well. Okay, and then we're combining both of those using plot underscore grid. Okay, plot underscore grid of course is part of the cow plot package that we talked about in the past. Okay, so what is the result of these two commands, these two plots? As I mentioned, the first plot just focuses on the actual coefficients themselves. Okay, we have on the x-axis we have the intercept itself with a point estimate of around 0.68 or something along those lines, and then we have our feeling thermometer with a coefficient for that feeling thermometer variable, which is around 0.13 and something 135 or something like that maybe. And so the question is then, what do these coefficients tell us? We can also actually go back, of course, and we see this is exactly 0.13 and minus 0.68. Those are the coefficients that we initially estimated. Okay. So the question now is, what does this actually mean in terms of fitting this logistic curve to our data? And this is what we can see in the second plot, where we basically took those coefficient estimates and plugged the linear predictor into the link function, into the inverse logit link function, and add this as well. We have our binned averages for subsets of our data, conditional on ideology as well. And we see now that this logistic link function, basically this logistic curve fits these data quite well. We see, of course, an increase with more conservative feeling thermometers, an increase in the probability to vote for the Republican candidate, and the logistic curve that we actually fit based on these data actually kind of fits at least those binned averages quite well. Okay, so that gives us already some indication that this logistic curve actually, kind of provides a better model of the underlying data generating process and a better model of the underlying predicted probabilities of observing a 1 rather than a 0 than for example the linear probability model that we saw earlier, where we saw these out of bounds predictions, but also in general not great conditional averages, so not a great prediction for the actual expectation of our outcome measure. Okay. So this is our basic logistic curve based on the fitted model that we have based on our point estimates. Of course, the next step now is to include estimation uncertainty, right? We talked about this in the context of linear regression. Of course, we don't know for certain that these are the true, values of our, in the population, and there is uncertainty around our estimates, okay, sampling uncertainty, estimation uncertainty, and so on. So in order to kind of visualize the uncertainty, we can directly leverage the fact that we're working in a Bayesian framework, so we directly can rely on the samples from our posterior distribution to basically not only work with one set of point estimates for our slope and our intercept, but actually use a vector of parameters that are basically drawn from the posterior distribution and give us a sense of the amount of uncertainty in our estimates. Okay, the way we can do this directly in R is to convert our model output into a tibble. So this will then turn into a 4000 by 2 matrix in this case for 4000 draws from the posterior distribution and 2 parameters that we're estimating, just the intercept and the slope. And we're taking a random sample of 500 draws from that larger matrix. The reason is that we don't need all 4000 draws from the posterior distribution. Just 500 draws in our case, or 100 for that matter, would be enough. Okay, and basically what we're doing is we're using the initial first plot that we had here, where we just had our 1 point estimate for our intercept and our slope coefficient, and we're adding additional points here to that plot itself. Now using our draws from the posterior distribution and to a underscore coefs, those are now those 500 draws from the posterior distribution. Each draw consists of 1 intercept and 1 slope coefficient, so to speak. Okay. And we're just adding that, okay? And then we are, we also want to, we don't only want to include uncertainty in this first plot, we also want to include kind of uncertainty for our actual logistic curve. So we want to draw basically one logistic curve for each of those draws from the posterior distribution, okay? In order to do that, we are going to use our posterior underscore epred function. And I will talk later in a later video a little bit more about comparing these different posterior simulation functions and explaining those differences. But just for now, posterior underscore epred directly basically gives us the conditional probability for a set of predictor values. Okay, the set of predictor values here that we're gonna compute those predicted probabilities for are basically the range of values for the feeling thermometer, the ideological feeling thermometer, ranging from 0 to 100 in steps of 1, right? So we basically have 101 feeling thermometer values that we're looking at here. And for each of those 100 steps, we're computing basically the predicted probability. So computing the linear predictor, plugging that into the link function, but now taking into account this uncertainty around our estimates, basically taking for each individual predicted probability, for each individual value of this predictor, we're basically taking into account a vector of parameters, a vector of coefficients that we estimated, right? So we don't only have basically one vector of predicted probabilities for each of those values, but we have basically a set of several predicted probabilities for each of those individual values, okay? The number of these predicted probabilities is again equal to the number of draws from the posterior distribution. We don't need all 4,000. What we're going to do here is we're going to take this matrix of predicted probabilities for these sets of values, and we're taking a sample of 10 because we just want to draw 10 different logistic curves. Otherwise the plot will just be we're just drawing curves over each other, and that's not really necessary. And we're doing a little bit more data munging to kind of get it into a format that we really want. We're adding our values of the independent variable in this matrix of predictions as well, and then converting it to a long data frame in order for it to basically to be able to add it to our initial plot that we had here, that we started with, okay? All right. And then the next step is just to, again, add those two plots, P1 and P2, in a grid the way we had it before, okay? And now we see how this plot basically changed. Instead of this 1 point estimate that we had here in the center initially for our intercept and our feeling thermometer, we now have this basically set of points that are all draws from the posterior distribution. So this gives us both an idea of the uncertainty around the estimates, both for the feeling thermometer as well as for the intercept, but also the covariance of those two parameters, okay? So this kind of already helps us kind of visualize the uncertainty around our estimates, but of course ultimately we're not interested in the parameters in the linear predictor itself, but we're interested in the resulting logistic curve, right? And in order to visualize that uncertainty, we added these lines based on our posterior epred output, okay? And we see now that in addition to this point prediction logistic curve, we now basically have a set of 10 logistic curve that vary, and the reason why they vary is due to the estimation uncertainty in our beta 0 and beta 1 coefficients, okay? All right, I'm going to take a break here as well, and in the next video I'm going to talk about logistic regression with multiple predictors and how to visualize those.